Whoa, fancy. Nope. What is it doing? Why are you doing this? Okay, cool. Well, just figure out this. Hey everyone, gonna start off our course in third semester calculus by talking a little bit about vectors. So, vectors, kind of just thinking about it from the purely mathematical standpoint, are directed line segments, right? They essentially get us from point A to point B. And the thing is, these 2 points, which we call the initial point and the terminal point, can be in a plane on a piece of paper, painted on a wall, on the floor. We could also have 2 points in three-dimensional space. We could have 2 points on a single line, right? The thing is, these 2 points that connect the start and the stop of this vector can be in any number of dimensions, right? Which is one of the big ideas in this course, is that everything that we learned about calculus in the XY plane can, one, be extended in its own way to multiple dimensions, two, has its own quirks when we extend to multiple dimensions. So, without further ado, vectors, directed line segments, they can represent a number of things. If you study physics, engineering, even chemistry, they can represent pathways like actual positions. They can represent fields of basically any kind of speed. You could have someone running a course. If you ever look on the TV watching the weather and you see wind graphs, that's another example of, well, that's actually an example of a slope field, but all of the little arrows you see are vectors. Um, Basically everything that you heard about magnitude and direction essentially comes down to this idea, right? The vectors in math are viewed as directed line segments, but when extended outside of math, can represent anything that has a strength or magnitude and a direction. To start off, let's draw a vector. So we want to draw a vector from point A to point B. So first thing I'm going to do is draw my initial point A, which I get from the nomenclature. Since we named the vector AB, we assume A is the starting point and B is the ending point. But also in the language, from A to B. Yeah, so the point A is the coordinate 1, 2, can graph it there. The point B is the coordinate 4, 4, so go over 4, up 4, and plot the point there. And when I draw the segment that connects these two, and I draw an arrow that indicates the direction I'm going, that is a vector. So initial point was 1, 2, terminal point was 4, 4. Magnitude and direction. So before I get into that, let's let's think a little bit. Two vectors are said to be equivalent, equal, same, if they have the same magnitude and the same direction. What I mean by that is the magnitude we can think of as the length or the distance from point A to point B. Right? Depending on what this vector represents, that could be a speed, it could be a distance, it could be a force, a weight, a current, right? Anything you can think of that has, again, a strength and a direction. So this vector is no different than if I were to take A to be the origin and B to be a point that I can arrive at with the same steps. Meaning I start at A, I go over and up. So notice I had to go over 3 units, I had to go up 2 units. So AB, the one we've drawn here, is equivalent to a vector that actually starts from the origin and goes out to the point 3, 2. Pretty interesting stuff. And we know that that's true because, again, two vectors are equivalent or the same if they have the same magnitude in the same direction, right? If I were to draw a line segment from the origin to the coordinate 3, 2, that would have the exact same length and it's going the same direction. When I say direction in the plane, I mean the angle that's made with the positive x-axis. Right? If I have something that starts when I'm not at the origin, just think of it as the angle it makes with the horizontal. So for that reason, when we represent AB, we actually come back to this idea. Now, a little bit more on magnitude and direction. The magnitude, as I mentioned, is going to be the length or the distance from point A to point B. But again, depending on what this vector represents, it could be any of these things. Magnitude, we can actually get using Pythagorean theorem. If you look at this picture that I've sketched out here, since this is horizontal and this is vertical, I know this is a 90-degree angle, which means that if I know two side lengths, I can find the third one using Pythagorean theorem. Yep, that's right. So the magnitude I can actually get from a squared plus b squared equals c squared, right? Rearranging that, we know that the hypotenuse is going to be equal to the square root of the horizontal length squared plus the vertical length squared. Notice I'm using 3 and 2 here, right? The difference between x's and the difference between y's. So when I do all my simplifying for that, I end up getting square root of 13, which is 3 point something, 3.6, 3.7. Anyway, that's the magnitude. Now the direction we can get using basically trigonometry. All right, now the direction, again, is the angle that's made with the horizontal, right? Basically from the right side horizontal. So if I have a triangle like the one I've drawn here, I know that tangent of this angle, which represents my direction, is 2 over 3. So for the direction, we know that tangent of the angle is 2 over 3. Opposite over adjacent. SOHCAHTOA. So I know that the direction, typically represented by the Greek letter theta, is equal to inverse tangent or arctangent of 2 over 3. Right? And using technology, we could actually get a radian measure for that. I say radians because this is a calculus class, meaning we don't really do anything in degrees. So if I were to type that into a handy dandy calculator, I could, in essence, get a number for that. Right, so we've got the magnitude, we've got the direction, we've got our terminal point, our initial point. We also saw that this vector that we drew is equivalent to a vector that starts at the origin and goes out to the point 3, 2. Before we talk about representation, as a side note, because edge cases are important to understand. There is something called the zero vector. We represent it using the number 0 with an arrow on top. Arrow usually just means vector quantity. So the zero vector is essentially any vector that has the same initial and terminal point. So if I were to graph it on a 2D plane, that would literally be a dot. If I were to graph it in three-dimensional space, it would be a dot. On a line, it would be a dot, right? Same initial, same terminal. So I bring this up because when you learn about different properties of vectors, this guy's mentioned a lot, and here you kind of gain an understanding of what it means. Okay, so representations. There are two ways that we could represent this vector AB. One is using pointy brackets. So the pointy bracket for this one basically separates into our two components. We have our horizontal component and our vertical component. So horizontal component would be 3, i.e. the change in x. And the vertical component would be 2, i.e. the change in y. So we could write this as the vector 3, 2. That's one way we can represent AB. This is equal to a vector quantity. Okay, and notice this kind of links back to this. If I had my if I had my starting point at the origin and I had my terminal point elsewhere so that the vectors were equivalent, right? I basically get this form, and this is what you'll see. You typically won't see stuff like this where they give you a start point and an end point. That really was just to show you what a vector is and how you can find this representation. For the second component, or for the second way, it's also going to separate into components, right? Our x component, our y component, but we use a different notation. For the x component, we have our change in x, and then we write I with a little hat. You might sometimes see it written as a little arrow, right? This just means essentially that you're giving the x component before that. Plus, and then our change in y, 4 minus 2 times j. Again, with a little hat, sometimes with a little arrow. So this we also might write as 3i plus 2j. That is another way to represent the vector AB. So officially, because this concept is also important for us to understand, I is a unit vector in positive x direction. J is a unit vector in the positive y direction. Yep. So what do I mean when I say unit vector? A unit vector is essentially a vector with the magnitude of 1 or length of 1. So essentially the i's and j's, imagine you're starting at the origin here. I goes exactly 1 unit in that direction. J goes exactly 1 unit in that direction. So if you think about it, I and j are essentially the basis, which you'll learn way more about in a linear algebra course, of the entire xy plane, right? This kind of sets up your Cartesian coordinate system. It's like when I just started drawing this, I had to draw through I and j, which is why we use them to label the horizontal and the vertical components. So that's what a unit vector is. Um, Other kind of side quest here. Yeah. Other kind of side quest here. Write a unit vector in the direction of AB. So this is also kind of a common thing that we see when we learn about vectors. If I want to write a unit vector in the direction of anything, right, I can maintain the direction and change the magnitude if I multiply both components by the same number. Specifically, if I multiply by 1 over the magnitude. So we know from back up here that the magnitude of the vector AB is square root of 13. We're going to write that fact here. Side note, whenever we write magnitude, we use these double bars. You might also see just regular absolute value signs used. But this notation means magnitude of the vector AB. So we got that, just to remind you, from our Pythagorean theorem. Square root of 3 squared plus 2 squared. So once I have my vector in component form like this, I can just use those numbers to find the magnitude. So that's the magnitude. The unit vector in the direction of AB is essentially going to be our component form divided by the magnitude. And to check our work, you could also test it, right? If I were to square this, so checking our work, if I were to take the square root of this component squared plus this component squared, I would end up with the square root of 3, actually no, 9 over 13 plus 4 over 13. Well, if I add 9 over 14 or 9 over 13 and 4 over 13, that gives me 13 over 13, which is also known as 1. So you see, when we go back and find the magnitude of the vector, we end up getting 1 because we made this have a magnitude of 1 by dividing each component by the magnitude of the original. Next little subtopic here, multiplying by a scalar. So vectors can be multiplied, added, subtracted, divided, and multiply is a very sticky word, as we'll learn in a couple videos from now. All right, but first one I want to focus on here is multiplying by scalar. So just to remind us, the original vector AB is 3, 2. And if I were to graph AB, I could start at the origin. I could go over 3 units, I could go up 2 units, get to my terminal point, and this represents AB. So if I were to multiply the vector AB by 2, I would get another vector, specifically one where these components are each doubled. So if AB is 3, 2, then 2AB is 6, 4. And if I were to draw that out, I would get that vector. Now negative, oops, it should be negative 1/2 AB. Nope. Negative 1/2 AB, I would essentially multiply both of these components by negative 1/2. So instead of 3, I would have negative 1.5 or negative 3/2. And instead of 2, I would have negative 1. So to graph that, I would start at the origin and I would go back 1.5 units. and down 1 unit. Start to finish, that would be -1/2 AB. Notice it goes exactly in the opposite direction as AB, and it's actually half the length of AB. So now we've got multiplication by a scalar. Next thing, adding vectors. So for this last bit, we're going to look at what happens graphically and component-wise when we add two vectors together. So let's say that I have two vectors, P and Q. So P, I graph these in blue. Yeah. So P is 3i minus 2j, which means if I start at the origin, I'm going to go to the right 3. I'm going to go down 2. That's the terminal point for vector P. Then for Q, I plus 5j, I'm going to go over 1 and up 5. That's the terminal point for Q. So we have P right here, and we have Q right there. So if I wanted to add these two vectors, here's what's going on geometrically. Imagine that these are two sides of a parallelogram. Parallelogram could be a rectangle, parallelogram could be a square, parallelogram could be slanted. The point is that these are two sides. I can draw the other two sides of this parallelogram in by kind of matching the slope. So here I had to go down 2 over 3. So if I go up to Q, I can go down to over 3, and that gives me this point. So I'm going to draw that side. And that kind of gives me the opposite side of vector P. And then I can do something similar for Q. I had to go up 5 over 1. So I'll go up 5. That'll bring me up to 3. And over 1 will bring me over to 4. So if I were to draw that out, you see how that makes a parallelogram. Now, if I were to draw from the origin where these two vectors meet, I would end up getting a vector that looks like that. Let's do a little math here. If I were to add these two vectors together, the resulting vector would have an x component of 4, right? That would be 3 plus 1. So 4i. And a vertical component of positive 3. Yeah. Vertical component of positive 3. So plus 3j. If I were to go oh, yeah, I see what I did. There it goes. It's not entirely parallel. Yeah. Okay, my bad. That's a much better parallelogram. Yeah. All right, so if I go, yeah, what ended up happening is I only went over 2 instead of 3. Yeah. Okay, so essentially what I want us to notice here is that when we complete this parallelogram, the point that we end up getting as our terminal point matches exactly what we would have got from just adding the horizontal components together and adding the vertical components together. So I end up getting 4i plus 3j. That's the component form. This is what the vector looks like. And it's the equivalent of adding whatever these two vectors p and q represent together. So it might be that I'm adding two forces together to understand what their net force is. It might be that I'm adding two speeds together to figure out what the resulting speed of something else is, right? Um, but that's going to end up giving me this component form. And the sum of these two vectors, when we do add them together, what we got, p plus q, is called the resultant vector. So essentially, if I had two objects that were providing a force in this direction, or in these directions, the net result would be that the object would move in this direction, exerting that force. And in the next video, we'll do some examples that kind of go over this.